G'day chemistry students. In this video, we're going to be looking at dot point 3.2.5, which is all about constructing galvanic cells. Let's get into it. Now, this is an example of a galvanic cell. This diagram looks quite complicated. There's lots of moving parts, but it's actually quite simple, and I'd like to break it down with you now. So in a galvanic cell, what you can do is make these two half cells and fill both containers, both half cells, with a solution that contains a different metal. So in this one, we have zinc sulfate and copper sulfate. You can then put in two metals that match the metal that's in solution into both of those half cells, and then connect the electrodes, we call these pieces of metal electrodes, I should say, connect those electrodes and connect them with a wire, and then also connect the two half cells of solution with a salt bridge. And what actually ends up happening is that you can get a full flow of electric current, and that is caused by a oxidation reduction system that sort of exists, where one half cell will oxidize and one half cell will reduce. Now, we're going to actually be making a bunch of these cells and playing around with them and taking measurements of their voltage, because depending on the combination that you have, you'll actually end up getting different energies or different amounts of voltage. And I guess that really is the simple setup. So what I want to do from this point is really just sort of explain why the process actually happens. And it goes all the way back to our reactivity series of metals. So if we look here, what we'll see is that zinc is more reactive than copper, which sits down at the bottom of the reactivity series. Now, because zinc is more reactive than copper, it undergoes oxidation. It's trying to push away and give away its electrons. And because of that, because the zinc is more reactive and wants to give away its electrons, the copper in this system is actually forced to take them up. So again, the metal that's more reactive gets its way, it gives electrons away like it wants to, and because it's more reactive, can force electrons upon the more non-reactive substance. So we have oxidation happening with the more reactive metal, and the side that oxidizes is known as the anode and has a negative charge because there's lots of electrons being produced. And then we also have the cathode on the other side, the half cell with the least reactive metal in it that undergoes reduction. So that cathode has a positive charge because it's capable of attracting these electrons here. So because the zinc electrode is producing lots and lots and lots of negative charge, what's going to end up happening is that zinc 2+ is also going to be formed. Some of this zinc that was solid is losing its electrons, which means that the zinc can't hold all of itself together, and you end up with excess zinc being pushed out into the solution. Now, if this side here has a positive charge, the salt bridge that we talked about before will end up trying to move negative charge to balance out the difference in charge that we've got here. And if negative charge is being moved out, then positive charge is moving sort of towards the opposite direction, or there'll be less negative charge towards this side of the half cell. And what that means is that these copper charges don't exactly want to be hanging around anymore, and they'll end up jumping onto or jumping towards the copper electrode, which is really good because they'll also be attracted by incoming electrons. And so they will pick up electrons that are coming around the wire that are being attracted to this positive side of the galvanic cell, and will end up forming copper solid. Now, that explanation is probably something that you need to hear a couple of times before it all sort of starts to make sense. So by all means, come to me with questions about that concept and about how the ions all move around and how the electrons all move around. But what I'm hoping that you can appreciate is there's a production of electrons on this side. They end up flowing towards the cathode side that's got a positive charge. And what's happening as well is that there is a flow of charge around this salt bridge as there are the formation and also the consumption of positive metal ions in each of the solutions in the half cell. So you end up having a full flow of charge, electrons up the top and ions down the bottom, which end up causing an electrical circuit, and that can supply power to all sorts of different things. We're just going to be measuring that power or that energy with a voltmeter, but this essentially is a really, really, really crude battery. You have chemical energy that's being stored here that can then get converted into electrical energy through the flow of electrons, and that electrical energy can then be harnessed to power electrical appliances. Keep in mind as well, a lot of the time cells get written up or described like this. So you have the solid metal, the solution that it's in, a double barrier marking the other side of the half cell, the solution, and then another line marking the distinction between the solution in the cell and the solid metal as well. Just got some examples here of some more galvanic cells that are actually used on a commercial market. So different types of batteries. So dry cells, these are like AA's and AAA's and D cell, C cell batteries, etc. You've also got button batteries as well, sometimes use silver, that sometimes use zinc. And then you also have different kinds of lithium batteries as well. And a lot of the time, these guys are rechargeable. And so depending on the chemicals that are present, depending on their construction, you have all sorts of varied types of cells, different types of batteries, which can produce differing amounts of electrical current and voltage for all sorts of uses. And each of them will have some type of cell reaction, which is a redox reaction in which there is a transfer of electrons. And keep in mind that between the positive and negative electrode, you've got electrons being produced, which are then flowing to the positive electrode. And in that flow that you've got when you actually complete the circuit with a wire, that electricity can be powering an electrical device as the electrons are passing from one side of the electrode to another. Thank you very much, everyone. In the next video, we're actually going to be doing some calculations around the voltage measurements that we'll be taking when we actually make some of these galvanic cells in class. There's actually a table of data in your data sheet which you can use to calculate the voltage of different types of galvanic cells. I'll show you some example questions to help you along in doing that. But until then, have a good one.